Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of PreCalculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the third part in a series on graphing using calculus, at least an introductory part to graphing using calculus. We have not gone over oblique asymptotes yet, and there's a little bit extra we need to do with symmetry as well. The example we're going to tackle in this video will be this function right here, f of x equals the natural log of 5 minus the natural log of x. We'll start with, as usual, our old school algebra skills. So the very first thing I look for is the y-intercept. Of course, in this case, you might be able to see it immediately. There is not a y-intercept because you can't allow x to be 0 because that is not in the domain of the logarithm. So there is no y-intercept. It just does not exist. Now we go to the x-intercepts. To find the x-intercepts, as we know from our algebra, we just let the output be 0, and you would solve this equation, natural log of 5 minus the natural log of x. Raise both sides base e, and you'll get 1, or e to the 0th, is equal to 5 minus the natural log of x. Adding the natural log of x to both sides, and subtracting 1 from both sides, we get that natural log of x is equal to 4. Raise both sides base e again, and you'll get x equals e raised to the 4th power. That is the x-intercept, the only x-intercept, in fact. So that's going to be e to the 4th, comma 0. Notice I keep it in exact form because, well, you would like to keep your mathematics as clean and as exact as possible. Off to the right, I'm just going to start building a table of values. X versus f of x here. Our x-intercept occurred at e to the 4th, comma 0. And now, let's see, we've graduated. We've gone through elementary algebra. Let's go into intermediate algebra, which is the domain of the function. Domain. So let's go back to the original function. I don't need all this algebra right here, so I'm just going to erase it. Just to let you know, don't do that if you're working at a college level class. You want to show all your work, so don't erase your work because you might make a mistake, and it's important that your professor sees that so they can help you out, or at least know that you know what you're doing and didn't just make up some random weird answer. Anyhow, the domain of this function, we've got two parts to our domain restrictions here. The first part is just like how you would do with any math course. You start with the innermost parenthesis and work your way out. That x right there, because it's nested within a natural log, must be strictly greater than 0. So that is one of our domain restrictions already, that x must be positive. But that's not the only issue. That natural log of x with the 5 there, 5 minus the natural log of x, is also nested within a natural logarithm. So not only does the x have to be positive, but 5 minus the natural log of x must also be positive. And if I add natural log of x to both sides of that inequality, I get that 5 has to be greater than the natural log of x. Raising both sides base e, you get e to the 5th. It must be greater than x. That is, x is less than e to the 5th, but greater than 0. Again, I'm reading it this way. X is less than e to the 5th, but it's greater than 0. So that is our domain. X must be between 0 and e to the 5th. It cannot include the edge points. So 0 to e to the 5th. Unfortunately, if you look at that, that looks like a point. And I really don't want to leave it that way just because I don't want people to think it is a point. So I'm going to say x is between 0 and e to the 5th. So that's our domain. Note that when you're doing problems like graphing using calculus, you're using all your algebra that you have learned in the past. We haven't even hit some of the top level algebra stuff yet, but it is important that you brush up on all your solution skills, whether it's solving trig equations or like this, logarithmic equations. You have to know how to do that. It's just a prerequisite for calculus, and so it's a heads up. If there's something that you know is a weakness, it's likely going to occur. So you should brush up on that material. All right. So let's see, we've gone through elementary and intermediate algebra. Let's step into pre-calculus and talk about asymptotic behavior. So there are two ways you can have asymptotes here. One is a vertical and one's a horizontal. So let's focus on the vertical asymptote. Well, we know the domain is restricted. So we likely have asymptotes at 0 and e to the 5th because we're dealing with logarithms. So you're going to look at those using limits because you're in calculus. You're going to just take the limit as x approaches 0, but you only need to do it from one side because your x values are limited to be between 0 and e to the 5th. So we only have to worry about the one-sided limit as x approaches 0 from above, at least for 0 there. And we'll take that limit of the natural log of 5 minus the natural log of x. Now, this is what I would consider to be a conceptual investigation of a limit. So if I were to take this x and allow it to approach 0, you would see that while this x value is definitely approaching 0 from above, that means that this logarithm, because we know the graphs of logarithms look like this. Well, if the argument for that logarithm is approaching 0, but from the right-hand side, its y values or its outputs are approaching negative infinity. So this natural logarithm is actually approaching negative infinity. But really, we're looking at 5 minus that negative infinity. And so 5 minus that negative infinity, all this picture right here, that is approaching positive infinity. 5 minus a negative is a positive, so positive infinity, and natural log as its argument goes to infinity becomes infinite. So we know that the vertical asymptote at x equals 0, that the function's going to jump up to infinity as x gets really close to 0. We'll look at the other vertical asymptote, which occurs at the other edge of our domain at e to the 5th. And we're going to do this way. We're going to just say limit as x approaches e to the 5th. And I'll put a little minus there, meaning that we're approaching e to the 5th, but from the left-hand side. And this will be of the natural log of 5 minus the natural log of x. Now, you do this, and the natural log of x as x is approaching e to the 5th is going to approach 5. Let me go ahead and circle that up. This will approach natural log of e to the 5th, which is 5, but not really. What's important here is what side of 5 it's approaching. Well, if x is getting close to e to the 5th, but from the left-hand side, if you think about a natural logarithmic function, it climbs forever and ever and ever. As our arguments get closer to e to the 5th, the output at e to the 5th is definitely 5, but as our arguments get closer to e to the 5th, the y values approach 5, but from below. That's critical. So it's approaching 5 from below. So it's like at a 4.9 or a 4.99. And again, that's critical because that means that this entire argument that I'm circling up in red is like a 5 minus a 4.99 or something like that. In other words, it's something approaching 0, but still positive. That's critical because the natural log cannot have a negative argument. Now we know, again, as the argument of the natural log approaches 0 from above, its y values or function values approach negative infinity. There you go. That is a conceptual investigation of that limit. No need to really do a lot of other type of like epsilon delta work or anything like that. You just quickly figure out the behavior at the vertical asymptotes, actually. That's kind of important. So it is a pre-calculus topic. Normally, vertical asymptotes are, but because we're in calculus, we should involve limits so we can figure out the behavior around those vertical asymptotes. The next thing you would normally do when you are investigating a function and trying to graph it is that you would go ahead and talk about the horizontal asymptotes. But heads up, horizontal asymptotes occur only if you have a domain that's infinite. It doesn't have to be infinite on both sides, but it has to be infinite at least on one side. And our domain is not. Our domain is restricted on both edges. So we're not going to have an end behavior here. So I'm just going to say the horizontal asymptotes don't exist. All right, so we're done there. Now we can step into calculus. I mean, we already did some with the limits there, but we can do a little bit more calculus here. So let's take a look at the first derivative. So the f is the natural log of 5 minus the natural log of x. So its derivative, f prime, is the derivative of the natural log, which is 1 over the argument. And the argument of our natural logarithm was this 5 minus the natural log of x. So we'll just write that down below. Of course, we have to invoke the chain rule here to take the derivative of the argument of that natural log, that highlighted piece. So what is the derivative of 5 minus the natural log of x? Well, derivative of 5 is 0, but the derivative of a negative natural log of x is a negative 1 over x. So we're going to attach this via the chain rule, a negative 1 over x. That's the derivative of a negative natural log of x. And now, there's not much else I need to do, because that is the derivative. I suppose that I could move that negative downstairs, and I could call this 1 over x times natural log of x minus 5. Basically swap the positions on those two terms. That way I get rid of that negativity. And then we need to talk about the signs of the derivative. So let's make a little quick sign chart here. F prime. Let's talk about where the derivative is undefined. So the derivative is undefined at 0, obviously, because you can't divide by 0, nor can you actually put 0 into that natural log. But note, 0 is not even in the domain of our function. So don't really get too freaked out about that open circle at the edge there. The domain of our function goes from 0 to e to the 5th. And so we're just looking for numbers that are domain issues between 0 and e to the 5th. Well, what else causes division by 0 here? Well, that natural log of x minus 5 can't be 0. Or in other words, natural log of x cannot be 5. Sorry, that was supposed to be an x. Natural log of x cannot be 5. But that just means x can't be e to the 5th, which we already have written down there. So that's not really helpful. Any other domain restrictions? And the answer to that is no. There are no domain restrictions otherwise. So we really don't have critical numbers for f on our domain. Our domain doesn't even include 0 and e to the 5th, so we don't have any critical numbers. That means that the derivative, f prime, is one sign the entire time. It's either always positive or always negative on this interval. So let's go ahead and just plug in any value on this interval that you want into the derivative. Make it nice for yourself. Try something like f prime of e to the 3rd. You may think that's not nice, but it is nice because the natural log of e to the 3rd, so we get 1 over e to the 3rd times, natural log of e to the 3rd is 3. Just makes it very easy. And so we have a negative number downstairs because that's a negative 2 times e to the 3rd. So, and there's a positive number in the numerator. So positive over negative, we know our derivative is negative, or in other words, that our function is decreasing on the entire domain. Now we can move forward with the rest of the problem. We didn't, by the way, create any new numbers. So we only have that one number so far on our table. Sometimes it just goes like that. Let's go ahead and take the second derivative. And if you take a look at our first derivative, the second derivative is going to involve a quotient rule. The derivative of the numerator is 0 times the denominator, doesn't matter, right? Minus the numerator times the derivative of the denominator. And that's going to be all over that denominator squared. I'm going to write it out just like this. Notice the domain issue is still the same as before. We can't plug in 0 and we cannot plug in e to the 5th. So we still have the same domain issue. Let's go ahead and take the derivative of this denominator right here as a product rule. So the derivative of x is 1 times the natural log of x minus 5 plus x times the derivative of that natural log of x minus 5, which is 1 over x. And now I'll clean this up. So the double derivative is going to equal, we have a negative times a natural log of x minus 5, but plus 1, so minus 4. All over x squared times the quantity natural log of x minus 5 to the second power. We're looking for places where the second derivative doesn't exist and also where the second derivative is 0. And I can't remember, but did I say that for the first derivative? I didn't. I didn't say it for the first derivative, but I should just mention this. When you're building this number line for the critical numbers of f here, you find the first derivative, and then you find where it's not defined, which was 0 and e to the 5th. But you also want to find out where that first derivative is 0. The reason why I didn't worry about that, didn't even have that discussion, is that the first derivative is a fraction, and the only way a fraction becomes 0 is if its numerator is 0. There's no way that numerator is going to become 0, so there's no place where the derivative would have been 0, so I didn't even think about mentioning it. The second derivative, on the other hand, while it will have division by 0 at 0 and again at e to the 5th, the second derivative will actually become 0 when natural log of x is equal to 4. So again, f double prime is equal to 0 when the natural log of x is equal to 4, or in other words, when x is equal to e to the 4th. E to the 4th actually is in this interval, and it's roughly, well, let's see, 81, 2, it's probably around, maybe about here, believe it or not. So that's roughly about where e to the 4th is going to be. So this breaks up this interval into two pieces. And we need to test both intervals, both sub-intervals there, to see what the sign is of the double derivative. Well, testing a number between 0 and e to the 4th, I'm going to test f double prime at e to the 3rd. Why? Because I can. That's why. So f double prime of e to the 3rd. This is a pretty nice one to evaluate. The denominator is always positive, so I'm not really worried about that. Some positive number downstairs. The numerator, though, you have a negative, and then natural log of e to the 3rd is 3 minus 4. So that's a negative, negative 1, or in other words, positive. It's a positive number. That's all I care about. So I know the double derivative is positive, so therefore the function is concave up, on this interval at least. And then pick any number between e to the 4th and e to the 5th. Well, you may think that you can't find one easily, but you can. E to the 4.5 is between e to the 4th and e to the 5th. The second derivative will always have a positive in its denominator, so I don't have to worry about that. And we have a negative natural log of e to the 4.5, which is 4.5 minus 4. That's a negative number upstairs. Downstairs is positive, so therefore our second derivative is negative, and therefore the curve will be concave down on that second interval. Pretty much that's it. Did we have an e to the 4th in our table already? Yep, we did. So there's no numbers to add to our table at all. Usually I have a whole list of numbers, like maybe 4 or 5 different points to plot, but this is just one of those cases where you have a very restricted amount of information. Let's go ahead and write or draw our two number lines up above for the first and second derivative. So you can see I have f prime there and f double prime represented. I'm just copying these that I wrote here. I know that the derivative is negative the entire interval, so the function will be decreasing. And I happen to know that partway through our interval, the second derivative will switch signs, and that'll be at e to the fourth. And e to the fourth is going to roughly be about a third of the way through the interval. So I'm going to go ahead and put it right around here, e to the fourth. And I'll go ahead and say it was, what was it? Positive and negative? I think that's what it was. Positive and negative. So it's concave up and concave down. Let me just double check. Yep. And so now that I have that, I can actually graph the function. I'll just get my ruler out again. And this time I'll put in a y-axis where I see x equals 0, which is right there. And I'll draw my y-axis in. Whoops. Don't mean to drag the entire screen to do this, but I keep doing that. All right, hold on. Those are my x and y axes. I'll just label them. That's x. That's y. I'm going to go ahead and draw in my vertical asymptotes. These are going to be my guidelines for graphing. Well, maybe I should plot my x-intercept actually, which occurred at e to the fourth, comma 0. So I'll just plot that right here. E to the fourth, comma 0. Which I kind of noticed in my previous videos. I kept saying I need to plot or label these points, and I never do. And it's only because I'm kind of rushing through. I don't mean to do that. But now I'm going to go ahead and draw in my vertical asymptotes, because those are kind of important to note so that everybody can see that we actually do have vertical asymptotes. I use red for vertical asymptotes. You could use whatever color you want. We have one there at x equals 0. It was supposed to be a 0, but for some reason it just didn't work out for me. And then we have another one at x equals e to the fifth, and I'm going to line it up with this right here, and I'll draw in x equals e to the fifth. There we go. I'll turn this off now. And this is x equals e to the fifth. So those are my two vertical asymptotes. We also have some behavior information around those vertical asymptotes. We know that as x is getting really close to 0 from the right-hand side, our function is going up to infinity. So I'm just going to go ahead and in blue graph that. My function is going to infinity right here. And then as x is approaching e to the fifth, but from the left-hand side, our function is diving down to negative infinity. So again, e to the fifth is a second vertical asymptote. And we know that our function is diving down to negative infinity at that point. Those are just going to be kind of reminders for me. Otherwise, the function is going to decrease the entire interval. It's going to be concave up until it hits this x-intercept, and then concave down. That's actually not too bad. We can pretty much freehand that. I know it's going to switch concavity right there, and that reminds me I should probably mention I do have an inflection point. So let me switch my concavity. It's a pretty long haul to get over to that point, but it looks something like this. Pretty decent graph. I mean, other than my jaggedy little scratches. Now, I should mention again that we do have an inflection point right here, because that's where the concavity switches from being concave up to concave down. Okay, so when you have a switch between concavity like that, it is an inflection point. I'll just even put an IP there for inflection point. Otherwise, this graph is completely done. So that is the graph of the natural log of 5 minus the natural log of x.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.